Okay, so in our last video here focused on chapter 19, really focused on kinetics of rigid body motion. Well, it's really the dynamics of rigid bodies in planar motion. We have a good example, and it's going to take us a little bit of time to work through. It's not that complicated of analysis, but it highlights some of the important aspects of considering both rotational and translational effects. Well, translational and rotational equations of motion, relating the forces and moments to the accelerations, both rotationally and translationally. And what it is, I got pulled two sample problems out of the book, and we're just going to do 19.91, and I'll talk along the way about how 19.92 differs. But what I just want to start here before we actually dig into it is that this is a very practical application of dynamics, right? So what we have here is basically two cars, and neither of them, well, one's parked and one's only moving 5 kilometers per hour, and so they keep this pretty low key so that this isn't going to be too dangerous of a crash. But in reality, right? So crash scene investigators can use dynamical analysis to they basically use the final state of two cars, so the positions of cars, maybe skid marks to get an idea of the path of travel of one of the cars. Maybe the skid marks tell us about the friction of the tires with the ground. Maybe they use video evidence to track that path. Whatever, right? They use all the known information they can get from the scene after the fact, or maybe if there was a video recording it. And they can then determine initial speeds, initial positions, what happened essentially in the crash, and if anything, who's to share the blame. Because in reality, right, oftentimes in crashes there's some sort of sharing of the blame, but maybe there's an 80% blame versus 20% blame to the other car. And so it's a real part of a real job is using this dynamical analysis for like the type of analysis we're going to do here. Okay, so we're going to ignore friction because we're saying there's an icy street, right? So the icy street means we can just throw out friction. And we're only going to analyze the motion in this x direction because basically assume that the collision happens with parallel-faced cars where they hit each other on parts of the cars that are vertically aligned, well, not vertically aligned, but up and down on the page aligned. And so the surfaces are in this plane about which the contact occurs, and the motion is therefore all in this direction. So that perpendicular nature keeps all the motion only in the x direction. But I just want to say these principles apply to the real world, and real crash scene investigators actually use a more complicated version of this analysis to basically make statements about 19.92. So in 19.91, we're given information about moments of inertia of the two cars, the masses of the two cars, and then we're given this thing called the coefficient of restitution. Okay, we'll talk about that along the way. That's kind of new here. And then we're given the geometry of the cars and the point of contact of the point of collision. And we're also given the speed of the speed of the two cars. This one's parked, and this one's moving at 5 kilometers per hour. All right. So we're basically from this setup, we would then want to anticipate something about the after the collision. So we're actually going to determine angular velocities and translational velocities of both cars afterwards. So we're going to determine 4 things. How much does this accelerate angularly, and how much does B angularly accelerate, and then accelerations both for both cars as well. 19.92 takes that in a little different way and says, okay, that's what we want to determine. All right, so the person driving car A claims to be moving at 5 kilometers per hour. We have now information about what B moves after the collision, whether that's from video, whether that's from determining it from where the cars ended up, right? So we know that the car moves at 1.7 meters per second. So that's, I would say, more realistic, right? So then you would do the analysis where the known information is one of the velocities afterward, and then we would want to determine this velocity as another input. Okay, so oh, and I said angular accelerations. I'm sorry, we're going to be determining angular velocities. So the quantities we're going to determine are the velocities, both angular and translational. So I just realized that because these are velocities given as, for 19.92, the known information now is a final velocity, and then we want to determine some of the initial things, right? Okay, we'll talk about that along the way, but just know that 19.92 is maybe more realistic in that you get information about after the effect. Maybe then you want to ask, how fast was the car moving? Does that mean that, who's to blame in this crash? Okay, so we'll only work through 19.91, and in that one we're given, well, in fact, whether we're doing 19.91 or 19.92, the following information is given except for the velocity. That's what will be different. Okay, so here the mass of car A is 1260 kilograms, and its moment of inertia about its center of mass is 2,400 kilogram meter squared, and mass of B is then 2,700 kilograms with a moment of inertia about its center of mass 7,600 kilogram meter squared. And let's see, we're given that this thing called the coefficient of restitution. Actually, we saw this in our linear momentum discussion. It's going to be a little bit, we have to be more careful with rigid bodies, and so we need more discussion on that. And then we're given that the initial velocity, or the initial speed here, is 5 kilometers per hour for car A, and also that velocity of car B is 0. And I'll just put the 0 meters per second. Okay. Now, velocity of 1 in state 1 of A, so before the collision, let's convert this to meters per second. So we've got 1,000 meters per kilometer. That's to cancel the kilometer in the denominator. And then we'll also multiply this by how many seconds in an hour. So we got to put an hour in the numerator, cancel, and we're left with 3,600. That's 60 minutes per hour and 60 seconds per minute. So 3,600 seconds per hour. And so we get that the velocity of the speed is 1.3889 meters per second. And this is a vector. So this is purely in the i-hat direction, in the rightward direction. Okay? So those are all the given quantities. We then want to find, for this one, the final velocities for, so final meaning at state 2, so after the collision, for A and B, and the final angular velocities, so in state 2 for A and B. Right, so two cars are gonna collide there. Can I just use pen caps? Right, two cars are gonna collide. What do we anticipate, right? Well, right, something, maybe they start kind of going off in this direction, right? So maybe is the intuition that, get out of here, the intuition that they both maybe continue to move forward, right? And because of this hitting here, they maybe have this rotation, right? Maybe does one get spun the other way, right? What is your intuition, right? So think about that. And then you can use that intuition at the end. Maybe your intuition was wrong and you need to readjust it, which is fine. Or maybe you can use your intuition to then say, oh, my math might have been wrong because I'm not getting my intuition, right? That's good to look at a problem before we start. Okay, let's talk about this coefficient of restitution. Okay, before we jump in, because this is actually needs a little bit more extension from our earlier look at this coefficient of restitution. Okay, so this, remember we said, is like a material property. It's a property of, the materials involved here. So recall before, when we had particle collisions, we had E defined to be velocity B2 minus velocity of A2, velocity A1 minus velocity B1. And that's actually, this could work here, right? Basically, that's going to give us one relationship between, well, the initial velocities that we know and the final velocities that we're trying to find, right? This is the ratio of relative velocities well, after 2 before, so after in the numerator and before. And so therefore, it's kind of a measure of how much kinetic energy loss did we have, right? So if there's like a less of a difference in the relative velocities, can be interpreted as a loss of kinetic energy. Measure the loss of total kinetic energy in the system. Okay, so that's what we talked about previously. Now, for rigid bodies, the definition we need to extend a little bit. Okay, so before I write it out, let me define a few things here. Okay, so let's draw a general picture. Let's actually have the bodies in collision, so at the state of collision. Okay, so this is A and this is B, and let's say that A, well, they just both have rotation. That's how, omega is rotating. And let's, just for simplicity, let's say they're rotating about their center of mass. And maybe this one's rotating backwards. Well, not backwards, just in the negative k hat direction, so into the page as the axis based on our right-hand rule. And right here at the point of contact, we'll call that point P. Okay? Well, at this instant, right, so before the collision, after the collision, let's do right after the collision. Let's say they're rebounding at this point. Let's say that the velocity, just due to this, motion and what motion the object had, so let's say, so if this is the rotation about its center of mass, let's say now this rebounds in, so if that's that way, yeah, let's say that this is just bouncing off here. So this is the velocity of A, and let's say that velocity of B heads off maybe in, well, it doesn't much matter, that direction. Okay. Oh, I did that the wrong. Okay, actually I can use this. This will work. I got lucky there. Let's say this heads off that way. Yeah, and so that would pull it a little bit backward. Okay, so these should all have. So this is the velocity of B. That I'm going to have to update. That's not just the velocity of B. I'm going to have to actually put, this is the velocity of B at point P, and this is perpendicular. So I'm going to subscript that with more things. I just jumped the gun on it a little bit. Okay, so let's describe what we have here. So with these velocities, right, I'm updating my notes here. With these velocities of the center of masses, right, we can come to this point, and how we define the coefficient of restitution is not these velocities, right? It's actually the velocities at the point of contact. And this is going to be that that issue we talked about last time, where if we don't define it this way, we're going to have to keep track of these center of masses as throughout the collision here, and it's easier to just use the point of contact, which is actually fixed during the collision, right, or during the time of the collision. Right. So let's say that, now pretend I hadn't written that yet, because what I wanted to do first is say, well, if this is the velocity of B, maybe our velocity of this actual point is going to be pulled a little bit inward, and so maybe the velocity of that there is then the velocity of B at point P, and then this would be the normal direction to the plane of contact. Okay, so it's normal to that surface of contact there, right? So that's a perpendicular velocity of point P there, right? Now, this then this is at the instant I guess the instant right after the collision, right? Then we could have something on this other side, so if that's rotating that way, this one is kind of heading off there. Well, it's normal, so this would be the velocity of A at point P, but its normal, its perpendicular component to the surface should always be equal and opposite there. That's the equal and opposite a result of kinematics here. So this is the velocity of A at P perpendicular. Okay, so with that description, now we have an updated, and our definition of coefficient of restitution has to get more complicated if we have a body, right? There's lots of different velocities at different points. What are these velocities here? What's actually the velocity of B, or one of the objects at that contact point P in the second state perpendicular, right? So we got so many subsets there. This is for the B object, right? And you can choose either one at the contact point in the 2 state, so after the collision, perpendicular to the plane of collision, all right? Minus the velocity for the other object at the collision point in the second state, so after the collision, perpendicular to the collision plane. And then at the bottom, right, we write A first at the collision point in the first state, so before the collision, perpendicular, and then B collision point before collision, perpendicular. So that, in general, is how we define coefficient of restitution, right? Oh, that's ugly. Regardless, this is still a ratio of relative velocities. So our interpretation doesn't change. Still a ratio of relative velocities after to before the collision. But it's at the collision point, so at P, the point of impact, and normal, only the normal to the plane of impact. Okay. Oh, and these aren't necessarily, these aren't the same velocities. They're not equal and opposite, but they will have, they have to be different, right, in order for us to have a difference here. They will be in the same direction, though, right? That's what I meant to say, right? So if this is the plane of, and so it's easy to compare them, right? They'll have the same directionality in opposite directions, right? So we're basically summing up those vectors, but only that component of the vector that's normal to the plane. For the entire system, we're summing it up. Okay, we're ready now to do our analysis here, now that we have that definition of coefficient of restitution. We'll start with, the free body diagram as always. Okay, and we're going to draw the free body diagram in 2 different views here. I'm going to try to keep this on here as long as we can. So our top view first, right, which is kind of that view we have. And so we'll draw car A, the one that's moving with its center of mass. And we'll put this close, but no, these are going to make contact here. And car B is not moving. And these actually, their center of masses are pulled towards the front, since the engine, which is typically in the front, pulls it forward. So really that one should have been a little bit more forward. But that's okay, right? The point of contact right there. So this is point P, this is point P. And the only forces here in this view is the force on A due to B and the force of B onto A. So we have 2 free body diagrams here because each one has its own. We would have friction on here, but there's no friction due to us being on an icy road, as given in the problem statement, right? Okay, maybe it might help here to also take a side view. Okay, so that way, because this isn't all the forces. We know that they weigh something, right? The cars weigh something. So if we took a side view here, here's car A as its center of mass there, and car B we'll put over here. It's a bit bigger, much bigger actually. And now in the side view, I like this one because it helps you see, you can start to think about moments and angular motion, but this one has all the forces on it. So that's why we did both, right? So somewhere on the side here at that point P is the force on A due to B. This is a force on B due to A. This one has a mass AG. This one has a mass BG, weight forces, and then we have a normal force, but no friction, right? Because we're neglecting that. Normal on A, normal on B. Okay, that's it. All right, that's good free body diagram. Okay, now we move into our equations of motion. Okay, the way we'll do this now is actually right, if we do summing the moments about point P, that's going to be a smart choice, right? Remember, what we're looking for is summing moments about a point. Look for a point where the moments sum to 0. We don't need to do this for the system as a whole. We can do this for each car individually, as long as we sum moments about the point P here, right? Look at this diagram, right? There's no moment about point P because the force acts at point P. Okay? And then we'll sum forces to 0, and that's a true vector for the entire system. All right, so we do have both linear momentum conservation and angular momentum conservation. So let's take linear momentum conservation first. Linear momentum is conserved, and that says that our and this is for the whole system, so we have MA VA1 plus MB VB1 equals MA VA2 plus MB VB2. That one's originally, so B is originally at rest, so that is 0. And right, so what is unknown here? Well, that's known, but we have two unknowns over here, the velocities. Okay, so this is our, also note here that there's only force, well, so there's right, there's only forces on each object in the x direction, well, or the let's see, on this diagram, this is I hat, j hat, k hat, and on this I hat, k hat, and let's see, we actually have j hat going into the board, right? Yep. For a right-handed coordinate system, you always need to cross I into j, and then k is a positive. So here we'd have to go I crossed into j, and then k. I crossed into j would be the. Nope. So that's why it's this way. I crossed into j, so k goes upward, right? So j has to be into the board. Well, we're just rotating the system that way, right? Okay. So hard to do these right-hand rules on these videos. All right, so we have x direction forces only here, at least on this plane, and so there's only motion. So cars move along x after the collision. All right, so another way to think about that, well, if linear momentum is conserved, if velocity is only in the x direction, then the final velocities are only in the x direction. All right, and if there's any, well, they could have components in the y direction and they'd be canceling out, right? But these forces are only in the x direction, so everything's going to go to the x direction. Okay, angular momentum is also conserved about point P for each car individually. All right, so this, let's take A first. For A, that means that the angular momentum about point P for A1 equals, for A at state 1 is, so that's before the collision, is the angular momentum about P for A at state 2 after the collision. All right, well we'll write this one out. All right, this is the position vector of A from P crossed into the linear momentum of A about point, well, about, yeah, so linear momentum, plus this is our rotational component here, or our, yeah, rotational component for that. And then this must equal the same exact thing, but in state 2, so after the collision. Crossed into MV A2 plus IA omega A2 K hat. All right. Anything we can cancel out here, right? So I'm just putting in the form for so angular momentum about a about a point P, and this is the full form. We have no rotation originally. All right, the car isn't rotating, it's just translating. These other terms, though, are in general non-zero, so we keep those. Okay, that's it. So now let's extend this for B. Do the same exact thing. HP B1 equals HP B2. So this is the angular momentum about point P for the B car before the collision and after the collision have to stay the same. That's angular momentum being conserved for point P. Because we're choosing for car B about point P, we're choosing that point because it's conserved. Well, we're originally at rest completely, so this is all the way 0. All right, think about if we were to write out this term, that would be 0 and omega would be 0 because it's completely at rest. So this one's nice. We have 0 equaling the position vector of B from P. And what we say B, right, that's to its center of mass, we should say, right? Crossed into the mass of B, velocity of B after collision, plus the moment of inertia for B, which is given to us in the problem statement, omega B2 k hat. Okay, and both of these are, in general, non-zero. All right. So now, this is it, right? Should we just count up our relationships here? Let's see. We've got one equation here. Well, actually, we have our coefficient of restitution too. So, well, we haven't written that out for this system yet, but we will in a second. What do we have right now? That was just a general discussion of coefficient of restitution. So we've got one relation there for two unknowns, VA2, VB2. We have another equation here, which is going to be, and we kind of have to expand this out, but that'll everything over here is known. That'll give us another relationship, but it introduces another unknown, which is omega. So we got two equations for three unknowns. This is another equation where both of these two are unknown. So this is a third equation, but now we have four unknowns, right? So that coefficient of restitution is going to be the fourth relationship that'll then let us have four equations and four unknowns. So let's let's get this. Okay, so the x components. Well, let's first simplify some of these relationships first and show how that'll show us how the coefficient of restitution is going to help us. So we first need the position vector of the center of mass of A from P. Okay, so back here, so we need to know to go from our center of mass to P. Well, back in the diagram, right? That's where the geometry. We need the geometry given there, right? So we're looking for the position vector from point P to A, to the center of mass of A. That's the relative position vector. So that is minus 1.7 in the I hat direction, plus 0.6 in the j hat direction, and those are in meters. Negative 1.7 starting from P, and then up 0.6 in j hat. Okay, so that means this term, where does this show up? That term right there? Actually, we see it twice. So there's this term and that term. Whenever we cross this relative position vector with, let's do it for A1, because we actually know that number. Well, this is just going to be VA1 is purely in the I hat direction, right? So we'll have we have a 0. Should we write it all the way out? Let's just write it all the way out. Minus, I don't have it in my notes, but I hat plus 0.6 j hat crossed into 1,260 kilograms, and then now VA1 is 1.3889 meter per second k hat. Okay, k hat. Okay, so when we look at this, right, this is just Oh, not k hat. I'm sorry. This is I read that this is I hat. This one is I hat. Let me sneak it in underneath. I don't know why I put k hat there. Okay, that's important though. I knew something was wrong because that would produce two components. We know that this should be well, we couldn't intuit that this is only going to have one component, right? So I hat crossed into I hat is no contribution, right? I hat crossed into I hat is nothing. So only this term gives us anything. This is j hat crossed into I hat. J crossed into I is minus k hat, and so this is going to be negative. In fact, it's negative 0.6 times 1260 times that number gives us 1050 kilogram meter squared per second k hat. Okay. Now, okay, so that's good. So now we have something to plug into here, and we can use the knowledge of what happened here to give us that relationship too, right? So the velocity at 2, so the velocity at p of 2, so this is our kinematic analysis here. Velocity at p for 2, we'll use our knowledge of what the velocity is at a, or at least the relationship, plus, and now we have the rotational motion. Rotation of a after the collision, okay, and then the relative position. So what we're doing here is the velocity of a at the collision point after the collision from its center of mass. Okay, this is now the velocity of a I hat, right? That's some good useful information that we know that this is purely in the hat direction, and that's 2 plus omega a2 k hat. That's unknown, crossed into 1.7 I hat minus 0.6 j hat. All right, and so this we can relate that the velocity for car A at the collision point after the collision is the velocity of the center of mass of car A plus 0.6 omega a2. So that's I hat. This comes from k hat crossed into j hat. That's minus I hat with another negative in there. So this is a positive. These are the I hat components there. And then this now is a k crossed into I. K crossed into I is in the j hat direction. That's positive 1.7 omega a2 j hat. All right. Let's see. What else can we do? We want to do the same exact thing. And the reason we're doing this, maybe we step back. Why would we be doing this? Why would we need the velocity right here? All right, we're getting the velocity for the individual cars at that point. That's because in order to use the coefficient of restitution, we need to get the velocities here. That's what's related in our coefficient of restitution. Okay, so we need this. So VB2 is going to be the velocity B2 plus omega B2 crossed into R relative position of the collision point with the center of mass of B. This is VB2 I hat plus omega b2 k hat crossed into, now we haven't done this one yet, position vector of P from the center of mass of B is negative 3.2 in the I hat, positive 0.6 in the j hat. Okay, all the way down here at the bottom. There we go. So our relative position vector there is negative 3.2 I hat plus 0.6 j hat. And so just like up above there, VB2, velocity for car B at the collision point for car 2 is going to be VB2 minus, right, so that's an I hat component. The I hat component is going to come from k crossed into j. That's minus I hat. So we get a minus 0.6 omega b2. These are the I hat components. Minus, because k cross I is positive j hat, so minus 3.2 omega b2 j hat. Okay, the reason we went through this work is this. We needed to do this to use this as our last equation. The fact that our coefficient of restitution is a half. We need this is given in terms of the tangential components, or sorry, the normal components to the collision plane at the collision point. So we needed the velocities at those points to use this relationship. Okay, so we'll come back to that right now. So we're going to use those calculations, and knowing that the x components, this is normal to the impact plane. The x components of above are related via the coefficient of restitution, E equals 0.5. Okay, so back to the original diagram, the collision plane is purely vertical, so the normal components of velocity before and after are these x components only. Okay, so when we write out, and back to our coefficient of restitution, it's these perpendicular components of velocity before and after that define the coefficient of restitution. So our coefficient of restitution, we know it's just 5, is going to be the horizontal component of b after minus the horizontal component of a after, and then we'll take the horizontal component before and subtract those. All right, so this is going to be VB2 minus 0.6 omega B2. That is our horizontal component before at point P. After collision at point P for the B car. Same thing for the A car. Its horizontal velocity at point P for the A car after the collision. And then we take the same things, but so the velocity for car A at point P before the collision, well, that's just how the center of mass is moving, right? Because there's no rotation. If there's no rotation and it's a rigid body, all points, including the collision point, are all moving together, and then minus 0 because car B is not moving at all before, and we know that that equals 0.5. So this now becomes our fourth equation. 4 equations, and if we let's do a summary of what we have. Okay, so we're done with kinematics because now we have 4 equations, 4 unknowns. Let me summarize the equations, right? You can see all I'm going to do is take this relationship, that relationship, and actually expand it, that relationship, and actually expand it, and then our new one, which is this relationship, and that's kind of already expanded, but we are going to move it around a little bit. Okay. So let's have a nice summary of our equations, keeping things organized. And along the way, it's important that we were just keeping track of how many unknowns we have so we know when we have enough information to go about solving the system. 4 unknowns, which are velocity for car A after collision, velocity for car B after collision. These are both for the center of masses. And then we have their angular velocities after as well. Okay, so from linear momentum, our relationship was MAVA1 equals MAVA2 plus MBVB2, which, right, well, this, let's see, MA1 is 1260 kilograms. This is 2700 kilograms. And this we know all of that. This is going to be 1260 kilograms times 1.3889 meter per second after we convert it. It was given 5 kilometers per hour. So those are all known. In fact, this number is 1750. Okay, and so here's our unknowns, where we know everything else. All right, let's see. What do we know from the angular momentum of car A? We know that the relationship looked like this, right? We determined that, well, this is the relationship, but then we calculated this to be negative 1050. Okay, so we have negative 1050 kilogram meter squared per second in the k-hat direction equals, and I'm going to plug some values in here. Okay, this is also going to be, no, I'm sorry, we're up here. Okay, we determined this cross product here turned out to be the j-hat component of that relative position vector, because all the motion is in i-hat. So when we come to here, velocity of a2 is also in the i-hat direction. So that's just going to be the 0.6, following the same procedure here, right? So this term is going to be 0.6 meters. Only that vertical change in the relative position vector. 1260 is the mass for car A. VA2, that's the only contribution to the k-hat component there. And then we have IA omega A2 k-hat direction. That one I kept as is. So now, well, that's that. This value out front here equals, this turns out to be 756. We'll put minus 756. And remember that this IA is 2400 from the problem statement. Okay, that's it. What we're doing here is just setting up a big system of equations, and I'll show you how to solve it once we have it all set up, really neatly organized. Okay, angular momentum of B, that relationship, where is that one? That relationship is here. Okay, so we got 0 equaling, and now if we expand this one out, this one's a little bit, so we're only going to take that vertical component, because all the velocities are horizontal only. We're only going to take that, the velocities of the center masses, right? We're only going to take that vertical component that contributes to the cross product. So that was 0.6 for this one as well, positive. Okay, whereas the other one was negative. So here we have 0.6 meters. The mass now of car 2 is 2,700 kilograms VB2 k-hat, and then the other term was IB omega B2 k-hat. So this product there is 1620, and this is given in the problem statement as 7,600. And that's it for that one, right? Oh, and I haven't been circling my unknowns. There's an unknown, there's an unknown, there's the unknown, there's the unknown. And then from our coefficient of restitution, E, we have, which is right above us here, all I'm going to do is multiply VA1 over, because that's a known quantity. Okay? So we have VB2 minus 0.6 omega B2 minus VA2 minus 0.6 omega A2. That's right up here. That's basically just distributing the negatives into the numerator. Pull VA1 over VA1. So this is 0.5 multiplied by VA1, which, well, we'll plug it in as one of these afterthoughts. This is 1.3889. So when we multiply it by 0.5, the whole term is 0.6944. And then everything else is known, or everything else is written in there. Unknowns are here. Okay. So, to me, 4 equations, 4 unknowns. I mean, a lot of these are relationships between 2 of them. You could easily express one, but it's not so clear how to go about this to actually immediately solve this, right? What I would do is recognize this as a system of 4 equations, 4 unknowns, and write it out this way. So we're going to express these 4 relationships. Let's see if I can fit it all on here in terms of matrices. Okay, I've gone a little bit off. I got a little bit, yeah, I think that fits. Okay. So what we can do is set up a matrix equation. A system of linear equations can always be represented this way. Okay, and it looks like this, right? So you put your unknowns here, velocity of A2, velocity of B2, angular velocity of A2, angular velocity of B. The 2's, remember, just refer to after the collision. Okay, and then we treat these as matrices. So coefficients on each of these are going to be this row, and then to the first equation. So the first equation looks like we have 1260 multiplying the first, VA2, 2700 multiplying VB2, and then nothing multiplying these two equals 1750. Okay, next equation, what multiplies VA2 is minus 756. VB2 is not in that equation. Omega A2 has a coefficient of 2400, and nothing, omega B2 isn't in that equation, and that equals negative 1050. All right. Next equation, well, I see that that's going to equal 0. The VA2 is not in that equation, but 1620 is the coefficient on VB2. Omega A2 isn't in that equation, but omega B2 is with a coefficient of 7600. And then this last equation, we got all four of them showing up here. So we've got a negative 1 by VA2. We've got a positive 1 for VB2, and then both of the omegas have a negative 0.6. And then that equals 0.6944. And now, right, we could right, whatever linear algebra technique you want to go for. It's setting up a matrix equation and getting into row reduced form, whatever you want to say. But this is a matrix 4 by 4. This is what we're trying to solve for, and that equals the right hand side, which is known. Right? This is solving a system of linear a linear system of equations that we need to solve. How I would do this, how I did do this, actually I did it on paper to prove that I could still do that, but that was after the fact that I had already solved it in a matter of seconds. I just went into Matlab, right? A nice solving, that is a part of our curriculum here at Montana State. In Matlab, I'll just tell you basically the setup. I defined a matrix called A equal this way, right? You go 1260, leave a space. 2700, leave a space. 0, 0, and then a semicolon to go to the next row. Minus 756, 0, 2400, and on and on and on, right? And you'd get a semicolon there. The last row, can we just do this all the way out? Put a 0, semicolon, a 0, 1620. This is all can be on one long line. 7600, semicolon, and then negative 1, 1, negative 0.6, negative 0.6. End your matrix definition, put a semicolon on the end, that suppresses the output. We then define B. That needs to be a vertical vector here, so that's going to be 1750, semicolon, to go to the new line. Negative 1050, semicolon 0, semicolon 0.6944. Suppress it, and then to get our answer, all we need to do, right, so theoretically, right, to get our answer, we just need the vector that is the inverse of a matrix product into B. Okay, and I'll give you the answer here in a second. In MATLAB, that comes from doing x equals inverse of a matrix product B. And don't suppress the output, because then that'll give you what this is. Okay, so here's my little bubble of solving it using MATLAB. However you do it, whether that's with a calculator, whether it's by hand, which can be a little bit ugly, we get an answer that is 0.1744, 0.5668, negative 0.3826, negative 0.1208. And the way we interpret this, right, these are the solutions for that in that order. Okay, so this is the velocity of A after the crash of their center of mass. This is the velocity of B's center of mass after the collision. This is the angular velocity of A after the collision. This is the angular velocity of B after the collision. And these are in, these two are in units of meter per second, and these two have units of radians per second. So this means, right, that both cars then end up moving to the right, but B moves faster. Let's check that, right? Does that make sense? Right, that means, right, 0.17 versus 0.56, they both move to the right after the collision. Okay, where were my caps? Okay, so after the collision, this is coming in slowly, and after the collision, this one moves faster. All right, that's what that means, but they both end up moving to the right, while they're both rotating in a clockwise direction, right, because they're both negative, and the first one rotates faster, well, the one that did the collision, the one that was originally moving. So while they're moving, I don't know if I can do both of these, this one moves faster, they're both rotating clockwise, right, and so they both rotate clockwise, and this one moves faster. This one on the right, or rotates faster. That's what we determined, right? Okay. Let's just write down those conclusions, and then we'll wrap this problem up. Both cars move right, B faster, and then both cars rotate clockwise, A faster. Now again, to wrap this analysis up, to then move into 19.92, right, which I started by saying, hey, that's maybe the more practical problem. You can imagine we would just redo the entire analysis. We'd get to the same system of equations here, but instead of B2 being an unknown, that would then be known, right? We're known that the B car, which is the Rolls-Royce here, moves at a speed of 1.7 after the collision. So, right? So instead, this becomes a known quantity, and we replace this with the unknown of what the original velocity of A1 is. So VA1 enters this, and you have a different, obviously the coefficients here would be different, the whole equations would be different, but the general setup and the equations of motion would all be the same. It's just like what's known and what's unknown. In fact, like, think right here, right? This would be unknown over here, that would be a known quantity. This would be unknown, or this would be, that would be the known quantity, and the unknown would be VA1. Right, so we'd put a red box around that. But it's pretty much the same procedure. You just have another system of 4 equations and solve it, right? And I think the answer to this one is that turns out that with 1.7, you can see here that with our analysis at 5 km per hour, this only moves 0.5668. Right? What 19.92 is like, well, it's actually 1.7 meters per second. Does that seem right? No. I mean, the car A had to be moving faster than the claimed quantity. Okay, so that's it for that was a good long example to work through here. Really, with these full momentum, analysis of linear and angular momentum. But that wraps us up, and we are now set to do the last part of the class, which is 3D kinetics, 3D dynamics.